welcome our users of Journal 5251. Today we're going to go over Chapter 12, which is the t-tests. I'm going to go a little bit quicker through the EDA, which is kind of at the beginning of each exercise, and then really focus on the t-test and what's happening there and what we can do for our analytical assignment, right? So I'm needing to load up my libraries and load in my data set as df so that the rest of the code works when I'm typing it in there. I've got dplyr and read Excel and ggplot2, and then I have my path here from the desktop, and I'm going to run that there. You can also, if you want to, go to your import data set, go to Excel. That's going to do the same things. We browse here. On the desktop, I have a messy desktop, but you can pick that there. Open. It's going to bring that in the preview. And then you have to make sure that you change this down here to df. Click on something else to make sure that this code changes basically to what I have here. And then you're going to import it. So now I've done this twice, but I can view it and make sure that I've got this in here. We're still talking about Washington Financial, but it's a little bit different data set today. And we get into the exploratory data analysis. So we're looking at a few variables, summary of our data frame, and the column sales in the thousands. So overall we can look at this, and then we're going to do it in a couple different categories here. So maybe we're interested in by promotion, so which campaign do better in the sum of sales. So this is the name of the data frame that we're going to create. It equals this, what we're about to do here. We're going to take our data set, pipe it through a group by promotion, and then pipe that through a summarize of what we're going to call sales, and that equals the sum of sales in the thousands. So hopefully you're still tracking on what that means each time, and then we can look at that in our output and we can see total sales in thousands per promotion. There's 3 promotions and we've got 1, 2, and 3. Looks like 3 did the best overall in total sales. Again, if you want to, and we'll do it in a little bit, you can group this by different things to see promos and age of store, or promos and market size, like we're about to do here in this next one. This is just a way for you to look at data and combine it in different ways. Here we have a plot distribution, and it looks like they're about evenly distributed for the total profits between those 3 promotions. All right, next one we're going to look at market size. So again, taking our data frame, we're grouping it by market size, and this time we're using summary of the count. So this is just how many observations fall within this grouped of market size. So there's 3 categories of market size: large, medium, and small. We're not super clear on what that actually means, but we can see the number of observations here that have that market size assigned to them. So there's 320 medium size, so that's the bigger portion of our audience, right, is the medium size market. Now we're going to look at market size per promo, and so this is just what I'm saying. We're adding our data set, we're piping it through a group by of promotion, which is going to have 3 options, and market size, which we now know is also going to have 3 options, and we're going to give a count of each. So we're looking at which market size got the most of promo 1 potentially. So I run that through and I'll get this little output. So now I can see, looks like promo 3 at the medium was the most, right? That's the most number of observations that we have there at 116. You can plot that out. Difference between these two, these are broken out with position of dodge, so be aware of that. This would keep these bars beside each other by market size. To see that in a quite slightly different way, we can do stack, position stack right here in our ggplot syntax, and that would put those on top. So now we're looking at promo 1, 2, and 3, and then these are all combined together in their total counts. Now we're looking at age of store. So this is a summary of just that one column there without any other group bys or divided by things. So our max store age is 28, our minimum is 1, and then our mean is about 8.5. Now we're looking at overall age. So we're just thinking about wanting to see how many stores are really at that max, how many stores are really closer to the mean, or maybe how many are brand new stores. So this is overall. Now we can see age of store at 1, there's 80. So that's probably going to be the majority of where our stores lie. Again, we can visualize that by looking at a ggplot. And now we can visually see that 1 week is really where the most stores are. And it looks like the majority of our stores fall below that 10. Now we're combining age of store and promotion number, and we're just given a count. That'll be in our output here. So promotion 1, and that breakdown here, and this is a bigger table, but we're going to look at it visually, and maybe we can get something out of it. I don't personally see any value in this bar chart, but maybe you can look at it and make some interpretations of the promotions that have gone out to those younger stores. Just a visualization there of what's going on. All right, then this tapply function is a new one that you might not have seen before. What it's actually doing, it's kind of functioning like a group by. So in the tapply function, we have the actual value that we're going to be applying the function to, and then we're going to have the group by. So we're looking at the promotion here, and then the function is actually summary. So again, we're going to get that min, median, and max here, broken up by promotion. So 1, 2, and 3 promotion, and then this is the age of store is the actual value that we're looking at. So it looks like promo 3 had the higher average store age. Alright, and I don't think that he has this one in later books, but he's got it in the text here, so I'll just run through and kind of show you by weeks of promo. And this is broken down mostly evenly, as you can kind of see there. They've ran these promos about the same amount of time. Okay, so now we're getting into the actual t-test and how this is working out. He gives a pretty decent explanation of how we do the t-test, but I just want to break down what he's doing in the RStudio code so that you kind of understand if you were wanting to do it manually, you can do it. But there's also one simple function that you can call to run your t-test, and it'll do it appropriately and kind of with a cleaner printout as well. So the first thing that we're doing is we're setting up our 2 samples, okay? And when we're running t-tests, we're comparing the means of 2 different samples, and we are trying to see if there is a statistically significant difference between these 2 different samples. So t-tests are used in a variety of applications. Here we're putting it to A/B testing. So we're potentially testing out a different promotion campaign, right? Does the text in this presentation do better than the text in this presentation of our communication, right? Are we sending out a better ad with this one? Does our website function better with this presentation or with that presentation? These are the types of questions that t-tests can address. So what we're doing here in the code is we're lining up 2 samples. So this is going to be our promo 1, And how it's created, we're taking our data set, that df, and this is a bracket, so we're actually pulling out a column. And so we're pulling out a column which that data frame of our variable promotion is equal to 1, and we want the sales in thousands. Okay, so think about this as you're trying to find a specific column, but you're setting a conditional for it. So this is the conditional of which. So right here we have sales in the thousands for those that have the promotion equal to 1. And so we're calling it promo 1. Same thing here with promo 2. We have sales in the thousands as our actual data, the values that we're going to have in these lists, filtered by those that in the promotion column or variable equal 2. All right, so now we have those two values lists. These are numbers. We can go down here in RStudio and actually kind of look at those initially. So we know that there's 172 values there, and there's 188 values here for promo 1 and promo 2 sales in the thousands. So we're trying to compare means and to see if these two samples are not just the same, right? We're always working against what is called the null hypothesis. And the null hypothesis is basically that there's no difference between these two samples. So they are potentially from the same population, or there's essentially no difference between one promotion, one text, one sample, 1A compared to 1B. Okay, so there's no difference if we do the website like this or if we do it like that. There's no difference if we have the campaign like this or if we have it like that. The difference is in the means. So right here, we're doing mean of campaign 1, and this is our call in R for mean of promo 1. So right here, boom, mean of promo 1, mean of promo 2. So now, in a simple sense, I could just compare those two numbers and I could say, oh, they look really far apart, so they must be different. Statistically speaking, that's not always accurate. Just because they are different numbers doesn't necessarily mean that there's a statistically significant difference. It could just mean that our sampling is not representative of the whole population. How the student t-test, as it's called, came about was really a worker from the Guinness Brewery. So this worker, engineer, if you will, was also kind of a mathematician. And these workers would publish papers on sampling processes. And they wanted to know if this sample of barley was representative of their whole batch, right? Could they count on the quality of this batch representing each one? And so they took out multiple samples, and they were trying to estimate the mean quality of the whole population or that whole batch of barley that they were going to brew with. That's kind of the initiating sequence of it. What he's doing here is he's actually filling out this equation for the t-test, which goes like this. Our t-value, which we're going to create, is the mean of sample 1 minus the mean of sample 2 over the square root of the standard deviation of population 1 squared divided by the n, or the total number of observations in sample 1, plus the standard deviation of sample 2 squared divided by the total number of observations in sample 2. Clear as mud? All right, that's what we're working with here, and it's a way to get at whether or not this sample is representative of the whole population as far as means go. And as we compare them, we're saying, could these two samples just be the same? That's our null hypothesis. And so whether we accept the null hypothesis, so we're going to say these two samples are basically the same. So we're accepting the null hypothesis, or if our p-value shows that we have statistically significant difference, which is typically at 0.05 or less, we're going to say we reject the null hypothesis and that these two means must be different. Okay, so as we build this out, we've got standard deviation. How we call that in R is SD on promo 1, SD on promo 2, and then for our sample size, we're actually using kind of a workabout here, and we're going to use length of promo 1. And so when we look in RStudio, we can actually see our length is 172. So we're just calling the length, and it's going to give us just that number, 172, for here, because we need that when we build out our equation. So length of promo 1, length of promo 2, it's going to give us 172 and 188. This right here represents df1 over 2, and that's actually degrees of freedom, and that's a way for us to determine our p-value or our statistical significance. In an intro to stats course, you would also have a t-distribution table, and you would have to go through your degrees of freedom, which is basically your sample size and how that sample size represents to the p-value there, and you find R is going to do that for us. And then also we have a little bit of a formula cheat here that he's created. So showing you this equation here and this equation that he's built up, we can see that this is the same equation here, and I'll walk you through the actual code. So t-value, t right here, equals what's about to come here. So we start our parentheses. We have mean 1, which we created with the mean. So that's this one right here, minus mean 2, which is that one right there. Close parentheses, divided by square root, SQRT, it's a square root. So this is representing this right here, the square root of, and then we need these parentheses again, the standard deviation of 1 squared, or n 1, which was that length that we created here, plus standard deviation 2 squared divided by the number of observations in sample 2. So he's recreated this equation here now in a manual way. So now let me run this straight here so that we can get a t-value. So now we have a t-value at the bottom of 6.427. This was just me running another way here. You can also write square root with that little hat symbol. So that will give you the same thing. We can print out our t-value and see that here. And so this tells us the relationship to the mean as a t-distribution. So if you remember from stats or from the reading, that perfect bell curve, 6.427 is kind of on the way outside, away from the mean of 0. So p-value, this right here, which means we're looking for a two-tail, because we don't know necessarily the direction always when we're running one of these. So this is the t-distribution table, a call on that. That's what that pt is doing. And it demands two things. It demands to know the t-value that you've calculated and the degrees of freedom. Now going back up here, the degrees of freedom, which I think, okay, I've already run. The degrees of freedom are your sample size in relation to the population, and it's a way that we control for the differences in the samples. Okay, there's a whole lot of mathematical proofs that go into that, but it's good to know that when you have two different samples, you're going to add them together and minus 2. So that's what we're done here. That length of 1 plus length of 2 minus 2. So we end up with that number 358, which is 172 plus 188 minus 2. So our p-value here, and then we're going to print it out at the end. So now this is telling us that our p-value is 4.14 e to the negative 10. So that means there's a bunch of zeros that are coming this here for. So our p-value is statistically significant. So we can say that campaign 1, which had the higher mean, if we remember, that there is it's a higher mean of, what are we looking for? Sales in the thousands for promo 1 compared to promo 2. With that statistically significant value, we can say we reject the null hypothesis. So we reject the idea that these two sample means are essentially the same population. We're saying that they're different, right? So we have one campaign that is statistically better than another campaign. Now in R, there's a lot of people that have run t-tests and want to do that a lot simpler. So this function has been created in actually base R. So a t-test, calling it the easy way, is just straight t.test, sample 1, sample 2. We can run that here. Bloop. And now it gives us this clean little printout here. And what this is actually, this Welsh 2 sample t-test, it's showing you the type of test that it ran. The Welsh is simple, meaning that we don't know if these variances are the same. And that's the default setting of the t-test function within R, and it's usually the best because we will often have different variances or different standard deviations between our different sample populations or our sample means. So right here, we've got the same t-value, and then we've got a slightly better p-value or slightly different p-value, and that's just because there was a different denominator for that equation that I showed you that we don't really need to get in here, but we can see in this printout that the p-value is statistically significant, and we can see that those means are different, and we can speak to, we put in promo 1 first, so that mean is higher. So we can interpret this as campaign 1 has a higher average sale than campaign 2. Okay, now we do the difference between promo 1 versus promo 3. Are these the same? So the hard way here, as we did before, so this time we're setting apart promo 3 as the sales in the thousands for those observations that the promotion variable equals to 3. That's what that promo 3 is. Then we've got all our same settings, the p-value we've done up here, and we can print out the p-value and see that doesn't mean 2. This means this is higher than 0.05. So we're looking at an insignificant. We cannot reject the null hypothesis that these two are different. Again, the easy way to run this here, we can see the mean of the first promo, so promo 1, the mean of X is 58.09. The mean for promo 3 is 55.3. And with this p-value, we're actually saying that we cannot say that these are statistically different. These means could have been pulled from the same population. Or if we're doing A/B testing, it means that these are essentially not different. There's no market improvement. There's no statistically significant improvement between using promo 1 over promo 3. And that is the whole display and what we'll be doing with t-tests on campaigns. The big takeaway here is to look at how we've separated these different run-throughs, because that's going to help you with your analytics assignment number 2.